I wish everyone a splendid day ahead. Today our speaker is Professor Susovon Samanta from NIT Rourkela. He is going to deliver a talk on efficient MPPT techniques for photovoltaic systems. Professor Samanta received the ME degree from Jadavpur University, Kolkata, India in 2003 and the PhD degree from Indian Institute of Technology, Kharagpur in 2012, both in electrical engineering. He is currently an associate professor with the Department of Electrical Engineering, National Institute of Technology, Rourkela. His research interests include analysis, modeling, and control of power converters used in photovoltaics, electric vehicles, and space applications. So, over to you, sir.
Good morning to all, and thank you for the introduction. Is my screen visible? PPT visible?
Yes, sir.
Okay. Okay. Good morning to all the participants. The topic that I want to discuss with you today is different MPPT techniques. Okay. So I hope that most of you are aware of these MPPT techniques and the application of MPPT techniques. So the outline of today's lecture is I will go through initially I will go through some basics, and then I will focus on the research work that we did and that was published in IEEE journals, their ideas, and obviously corresponding experimental results. So at any point of time, if you want to, if you are not understanding anything, you can interrupt me, and then we can have a discussion. So, I think there is no need of any introduction of the MPPT technique, because if you see the different applications nowadays, so you have maybe the on-grid solar system where you are using the net metering. You are install the solar panel in your rooftop, and then you are supplying the power to the grid directly. And from the grid, you are taking your power, and the difference is actually either if you have more power generated than the you consumed, then obviously you will get that money back. Now there is a off-grid solar system in some application in some areas where grid is not available.
Symbolic.
Hello. Has anybody?
Participants, kindly mute yourselves.
Okay. So in off-grid solar system, you don't have any grid, so you have only power is your source is panel, solar panel. But the main problem is obviously during night and during rainy season, where there is a level of irradiation is less, then you have less power available from the solar panel. So what you can do is that you can use a battery as a secondary source, and the combination of this panel and battery can be used to supply the load. That is basically your off-grid solar system. Now you can have a combination of that. Like you can have a solar panel, you can have battery, and you can also have the utility grid. Okay. And nowadays also it is very popular to have that EV charging facility in your home, or if there is a very huge community, then they are also using this EV charging, where the main source is basically panel and the grid. You can use a PWM rectifier convert AC to DC, and then you have the solar panel, which will charge your battery. So ultimately, all of these applications have the solar panel. Okay, so because they are one of the source. Now, if you go a little bit deep into this circuit, because it's kind of a block diagram, if you come to the corresponding circuit diagram, then for this grid connected system, we may have a single stage grid connected system, or we may have a double stage grid connected system. So ultimately, we need to have some kind of circuit power converter here. Okay, and this should do the following jobs, like MPPT. Then it should have a DC link control. Then it should have the frequency control and other things, grid synchronization, islanding protection, all these things. But obviously today's focus, or this lecture focus, is, as the name of the lecture, it is MPPT. So the idea of all these is you have a as primary source is solar panel, and you want to extract the power from the solar panel. Okay, and so how you can extract the power from the solar panel? You can directly connect the load, or you can have some power converter circuit. So before going to that, we need to understand the IV characteristics and the PV characteristics of the PV panel, cell, or array, whatever you can say, because cell is the lowest unit, you can say, and multiple number of cells can connect in series and parallel. Then it can have a panel, and multiple panels can connected series and parallel. It will form an array. So cell is the uh, basic unit. So this is also available in literature, and most probably all of you can know this one, that there are different kind of cell model available, equivalent cell model available, representing with electrical circuit component. So there is a single diode model, there is a double diode model. But as I said, our main focus is MPPT, so we'll quickly go through this one. So this is basically this constant current source representing the photocurrent, and this is the diode. So if I consider this shunt resistance initially as infinity and the series resistance is 0, then that is basically a ideal PV cell model. So ideal PV cell model, the IV characteristics of the ideal PV cell can be expressed as equation number 1, but it's very simple because this is representing the diode current. Okay, and this is your this cell current that is generated due to the irradiation. So you have a constant current, which obviously as it suggests, it depends upon the light. So it depends upon the irradiation. So its value can vary. But let us, for a constant irradiation, it will be a constant value. And this is your diode characteristics. And this current is nothing but this cell current minus the, if you apply the KCL at this point, the cell current minus this diode current. So ultimately, if you do this, you will get the IV characteristics of solar cell. Okay. And these are the corresponding constant. Now, because the solar cell has the junction resistance, and there are other losses which actually can represent with this shunt resistance and the series resistance. And as I said, also it is not only one cell. There are a number of cells which are connected in series and parallel to form a panel. So if I consider that in one panel there are, or if I consider array also, because here I'm mentioning array. So there are ns number of cells are connected in series and np number of cells are connected in parallel. Then obviously if you again use the KCL KVL, you will get this expression for a practical PV panel or PV array. Now there are two important points here, which will actually there are 3 points which are important to understand. One is this point, another is this point, and if you draw the PV curve, you can understand. If you draw the PV curve later on from here, so you can see that initially, so it will start from 0 because at this point, so this is your V is equal to 0 point. So that is why it is also at V is equal to 0. It is called short circuit current. And here your I is equal to 0. So it is also called open circuit voltage. OK. And if you just multiply, because power you will get by multiplying voltage and current at each point in the curve, you will get the corresponding PV curve. And you can understand from this curve that at this point you will get the maximum power. So ultimately what we want is that we want that the panel voltage should be at this point always if I want MPPT. So this is important point from where we will get the maximum power. This is the point where you have the short circuit current where voltage is 0. And at this point, you have current is 0 and you have the open circuit voltage. Now the question is that if I vary, because you can understand that the cell, the irradiation will vary. So depending on the irradiation, how this IV curve will move. And also irradiation, when the irradiation is changing, there is a change in the array temperature or PV panel temperature. So these are the two important parameters that we should understand, that how the IV characteristics will change depending on the irradiation and depending on the temperature. So first let us consider the short circuit point, like where your V is equal to 0. At this point, your V is equal to 0. So if I, in this expression, if I put V is equal to 0, then I is nothing but your ISC. So wherever there is a V, I will put V is equal to 0 and I is equal to is nothing but your ISC. Then the expression will become this. Now, from this expression, you can understand this is basically the reverse saturation current of the diode. OK, and this is RS VT. This is the thermal voltage. And this RS RP is the series resistance and the parallel resistance. OK, now these all are constant once you have the fixed irradiation. Another important point is that because RP is very high, OK, and I0 is very low. So this two term is actually negligible compared to this IPH because of this and because of this value. So ultimately what we can tell is that the short circuit current is proportional to the photon current, basically, which is depending on the irradiation. So as the irradiation will vary almost equally, the short circuit current will vary in the PV panel. OK, now let us try to find out the other point, like how the VOC open circuit voltage will change as per the irradiation. So to get that, what you have to do is that we have to put I is equal to 0 and V is equal to VOC. In this expression now, we have to put I is equal to 0 and V is equal to VOC in all the places where there is a I and there is a V, then we'll get this expression. Okay, and you can understand from this expression that the VOC is proportional to the thermal voltage, which is basically there is a depending on the temperature, which depends on the temperature, and it is logarithmically varies with the IPH. Okay, so that is why if I now try to draw the IV characteristics by varying the irradiation, you can see this kind of waveform IV characteristics you will get, where the short circuit current is proportional, almost varying equally with your irradiation, because irradiation is given in terms of watt per meter square. And your VOC is not varying like your ISC. This variation is very slow. It is actually varying, as we have seen, it is varying logarithmically. That is why this variation is slow, and this variation is basically as per the irradiation changes. So that is basically your solar panel model. So now we will discuss about that why we need a DC-DC converter, or let us say it is not only DC-DC converter, we can also use a inverter. But now today's lecture, I will only focus on the DC-DC converter and what topology of DC-DC converter to choose. Okay. Actually, we can, if we have a load, we can directly connect the panel to the load. So let us now see that one. Now, if I have a PV panel, I can directly connect a resistive load to the, if I have a resistance, resistive load, I can directly connect the panel to the resistive load. What is the problem with that? Why we need a DC-DC converter? Or say, for example, any power electronics circuit. Now, if I connect directly a resistive load to the panel, what will happen? The panel has IV characteristics that we have already seen. So this is your VPV and this is your IPV. Okay. Now, depending on the load resistance, so remember this is IPV. So whatever be the load resistance, what will be the operating point? Operating point, obviously, this is the panel characteristics. Similarly, we have a load resistance characteristics. Okay. So if I draw the load resistance, it is basically not resistance, it is inverse of the resistance like conductance, because we are plotting with the IV curve, not VI curve. Okay. So suppose example, this is by 1 by RL. So what will be the operating point at this particular irradiation level with this particular RL value? The operating point will be this, and obviously this is not the maximum power point that we have already discussed. Okay, but if I choose the load resistance in such a way that it is crossing exactly at this point or around this point, then we can extract the maximum power from the PV panel, because you know
ఫీడ్బ్యాక్ వస్తే నేను ఇలా పెట్టేసి వెళ్ళిపోతున్నానా, ఎప్పుడు వాడు స్టార్ట్ చేసేసాడు, మధ్యలో 2-3 అవర్స్ గ్యాప్ ఇస్తాడు ఎందుకు? 2:30 to 2:30 అంటున్నా 3 వరకు.
it is requested participants, please mute yourself, unmute only if you have any question, because otherwise it creates problem to me. Okay, so at this point, so if I have a load resistance which is crossing exactly at this point, then you can extract the maximum power. But again, the problem is that because due to when there is a change in irradiation, this IV will also change and your MPP point will shift. So you have to again change the load resistance. And you know the maximum power point theorem. Maximum power can be transferred from the source to the load when load resistance is equal to the source resistance. Okay. So this is the whole idea that we need to change the load resistance such that it will match, or rather I can say that load resistance and source resistance should match. Okay. Now, if I have a battery, so if I have a panel and I directly connected a battery. Okay. So if I have a PV panel where you have a VOC like around 20 volt, and if I have a 12 volt battery, then obviously IV characteristics of the battery will be, it is a constant voltage. So it will look like this one. Then you can understand that the crossing point will be your operating point. At that point, the PV panel will operate and accordingly it will supply the power. So to get the maximum power, I need to have this kind of battery. If I connect with this voltage, then it will give you the maximum power. Now you can also a little bit extend, because battery also is not a ideal voltage source. It can have some internal resistance, and accordingly this characteristics will vary, and you will get the corresponding operating point. And if you directly, because people are now connecting, if you directly connect a PV panel with a pump, then pump has this kind of characteristics where your voltage is proportional to the current square of the current. Then you have this kind of characteristics of the pump, and the operating point. Again, the operating point will be the intersection between the load and the source. So depending on that, you will have either this operating point or this operating point and this operating point. So you don't have any control over the operating point or where to operate. And for that reason, what you can do is that you can connect a converter in between your panel and the load. Then the next question is that what advantages we are getting by connecting the DC-DC converter. Now, so I have here describe about 3 different well-known converter, like if you use a buck converter, if you use a boost converter, or if you use a converter which is having this kind of characteristics. Okay. Now, if you have a buck converter, you know that your output voltage is D into input voltage, and your input voltage is nothing but input is now a PV panel. So it is your PV voltage, panel voltage. So that is why D is equal to V0 by VPV. Now this is important. Now input resistance seen by the PV panel. So that means if you see this diagram, so this is your load resistance. Now what will be the current? This current will decide by the input resistance seen by this PV panel. That means this load resistance will be reflected into this side. And what is the reflected version of the load resistance that is seen by the PV panel? So the panel sees the resistance, which is basically, I can say it is nothing but your panel voltage divided by the panel current. And panel voltage is nothing but your V0 by D. And if I consider a 100% efficient DC-DC converter, then you know that V0 I0 is your VPV IPV. And then you can say that IPV is nothing but your I0 into D. So if I place this VPV in terms of the output voltage, IPV in terms of the output current, then I will get this relationship. Then it is nothing but RL by D square. So the load resistance that is there in the output side, the panel is seen as RL by D square, where D is the duty ratio of that particular converter. Okay. Now you can see. So again, if I draw the IV character, so this is the IV characteristics of the PV panel. And now your PV panel is seen a resistance RLPV, which is nothing but your RL by D square. So this is your, obviously, as I said, it is IV. So this is the load line of 1 by RLPV. Now you can understand that by varying the duty ratio of the converter, you can vary this line. Okay. And by varying this line means you can change the operating point of the PV panel. That is the most important thing. Now for buck converter, how much I can vary? So for any converter, I can go from D is equal to 0 to 1 only. So minimum is 0 and maximum is 1. So if I have D is equal to 0, then what is the resistance seen by the PV panel? It is infinity. Infinity means it is open circuit. So this will be the point. Okay. And at D is equal to 1, that is the maximum duty ratio that I can go. This resistance seen by the PV panel is RL. So depending on the RL value, you can have this line. Now, say for example, you have taken a load resistance and that load resistance is like crossing this point. So this is your 1 by RL. Now, in this case, because sometimes students are saying that using a buck converter, I am not getting the maximum power because of this reason. Because if you have chosen the RL such that it is not covering the MPP point, then you will not achieve MPP. Never. Because if you take this RL, then at D is equal to 1, that is the maximum duty ratio you can go, you will get this RL. So this will be the operating point. It's much away from the MPP. Okay. So if you use the buck converter, it will the operating region is basically operating region is basically the lower side of this IV characteristics. So the same thing. So same thing I can see for a boost converter. I can apply for a boost converter, and then this is the resistance seen by the PV panel, and the relationship is RL into 1 minus D square. Now again, we can go from D is equal to 0 to 1 only. And for D is equal to 0, we will get RL. And depending on the value of RL, it may be here, or it may be here, or it may be here, this crossing point. And D is equal to 1, we will have a 0 resistance. That means it is the short circuit current. Okay, so it will actually cover the upper portion of the IV characteristics. So for boost converter also, if you choose the RL such that it is crossing at this point, this is the maximum RL that you have chosen, then you will never get a maximum power if you use a boost converter. Now, if you use the converters which are having this input-output relationship D by 1 minus D, then what will happen? Then the resistance seen by the panel is expressed as RL into 1 minus D square by D square. Now, if you see, if you put D is equal to 0, then you will have an infinite resistance. So this will be the operating point for D is equal to 0. And for D is equal to 1, this is 0. So this will be the operating point. So that means you can actually get the whole operating region of IV characteristics if you vary from D is equal to 0 to 1. Okay. So that is why there are some these Texas Instruments have this solar optimizer where they are using buck boost converter to get the whole operating region of the IV characteristics. Another important point I want to make here, because that will be useful for understanding the MPPT algorithm. If you see in all the converter, what is happening if I increase the duty ratio, because D is equal to 0 and this is D is equal to 1, your panel voltage is actually decreasing. Now see the boost converter. This is your D is equal to 0. This is your duty ratio is equal to 1. So if I increase the duty ratio, your panel voltage is decreasing. Now see in this case, this is D is equal to 0. This is D is equal to 1. Again, if I increase the duty ratio, your panel voltage is decreasing. So one point while using MPPT algorithm, we should keep in mind that if I increase the duty ratio, my panel voltage will decrease. And if I decrease the duty ratio, then my panel voltage will increase. Because that is the thing that you have to do. You have to you can either increase your duty ratio or decrease your duty ratio. So you should understand that by increasing the duty ratio, what will happen to the PV panel voltage, and by decreasing the duty ratio, what will happen to the panel voltage. So increasing duty ratio will decrease the panel voltage. Now we will discuss about different MPPT, like some well-known MPPT techniques. So this is fractional open circuit voltage, where you are basically, if you see the IV characteristics. So this is, as I said, this is my open circuit voltage, and this is my MPP, which is basically like you can say it is near about 80%, 78 to 80% of your open circuit. Like this voltage is nothing but approximately around 0.78 to 0.8 of your VOC. Okay. So what you can do is that you can take this VOC. Initially, you have the panel. You do the IV characteristics, because obviously VOC, as I said, depending on the irradiation, depending on the temperature, but you have to fix some VOC. And then this case like 78 to 80%, obviously as the life of the panel goes on, this point is also varying. So it is also not constant, but initially if you can take some constant value of 0.78 or 0.8, then this is your VMPP. Then you measure the voltage. You just check whether your voltage is greater than MPP value or not, because this value is fixed now. As I said, if my panel voltage is greater than MPP, then which side I am? If my panel voltage is greater than MPP, that means I am in the right side of the MPP. Okay, maybe here, because my panel voltage is more than MPP. Then what I need to do? I need to decrease the voltage, panel voltage. How to decrease? So if I want to decrease the panel voltage, as I said, I need to increase the duty ratio. So if you increase the duty ratio of the converter, it will reach to the MPP. So see, and obviously if I am in the left side of the MPP, then I should increase the panel voltage to go to MPP. That means I need to decrease the duty ratio. Similarly, you can use the that short circuit current, like that is fractional short circuit MPPT algorithm. What is the meaning of that? The same thing, because this is your ISC current, this is the maximum current, and IMPP current is somewhat less than the maximum current. So that is, you can check that, and you can use some proportionality constant here also. Okay, and then accordingly you can find out the MPP algorithm. But as I said, but when there is a change in the irradiation, or there is a change in the temperature during aging also, it will not give you the proper results. So what mostly people are using in almost all commercial application, they are using this perturb and observe algorithm, which is basically your P and O algorithm. So what is this P and O algorithm? So as I already discussed that your IV characteristics of PV panel is looking like this. This is your IV. And each point, if you multiply the voltage and current, then you will correspondingly, you will get the your power versus voltage. Panel power versus panel voltage curve. Okay. Now, interestingly, if you see in the left side of this curve, slope is always positive. Okay. And in the right side, slope is negative. Like if I want to move from this point to this point, then your power, difference in the power is positive, and difference in the voltage is also positive. So dP is positive and dV is also positive. Okay. And if I try to move from this point to this point, here also you see your dP is negative, del P basically, and del V is also negative. So del P by del V is always positive. If I go from A to B in this, so if I go from A to B, sorry. So this is A to B, where both are positive, and if I go from B to A, then both are negative, but the slope is positive. You can check with the right side that slope is negative. Okay. Now suppose I am, how to take the decision? I am at B. Somehow I reached at B, and I have the information about A. So already, as we have seen, that if I check the power, difference in the power at B, which is positive, difference in the voltage at B, which is also positive. So dP by dV is positive. So what is your say? That how to move? So ultimately that means this is my MPP point. So I am actually moving in the right direction. So I should continue to move in that direction. So continue to move in the direction means I should actually increase my voltage, panel voltage, to get at this point. If I increase my panel voltage, then maybe I will reach here. Okay. And so let us now, with this knowledge, let us now try to see this diagram. Suppose I am at point 1 and I have already seen I have reached the point 1 from this point. So at this point 1, we have already del P greater than 0, del V greater than 0. So we should increase the panel voltage. So we'll move to point 2. At point 2, again, you can see that your difference in power and difference in voltage both are positive. Okay. So again, I should increase the panel voltage. So I will come to 3. But at 3, if you see at 3, what is happening at 3, your power is actually reduced. So del P at 3, your del P is less than 0, but your del V is greater than 0 because still your voltage is increased. So as I said, if my dP by dV is negative, then what should I do? I should actually decrease my panel voltage. So I should decrease my panel voltage. Okay. Now you see at 2, what is happening? You are actually at 2, you have del P greater than 0, but your del V is less than 0 at 2 because you are reducing your voltage. So what will happen? So that means at 2, my dP by dV is less than 0. So as per the algorithm, I should actually again decrease the panel voltage. So I will come back here. And now here what will happen at this point 1, what is happening? Del P is less than 0 here and del V is less than 0. Both are 0. So I have a positive slope. So I should increase the panel voltage. So again, it will go to 2. So although this is your MPP point, but as it will never exactly, it will not stop at that point because that is the name. It is perturbing and you are observing. So that is why it is called perturb and observe, and then take your decision. So it will move, it will oscillate about this MPP point. Okay. So that is what this is the flow chart. Already I explained that if dP is greater than 0, dV is greater than 0, I should what I said, I should actually increase the panel voltage. So that means I should decrease the duty ratio. Okay. So this way, your MPP point is moving around the maximum power. And this, there is basically, this is kind of a 3-stepping. If you will see there is 3 voltage level. So there will be 3-stepping, although these and these are almost equal, or these and this may be almost equal, that you will see later on. Now, one of the important problem with this P&O algorithm is basically the drift. So let us understand what is drift. So this is so as we have already seen that if this is your IV characteristics for one irradiation level, if I increase the irradiation, your IV characteristics will shift. Okay. And as the current is increasing, obviously we'll get more power. So ultimately this is one irradiation level, the blue line, and red line is when you increase the irradiation level. Okay. So initially it is operating around 1, 2, 3, as I already mentioned, when there is a fixed irradiation. Now suppose consider that there is a sudden increase in irradiation. So you will get this value. When there is a sudden increase in irradiation at that condition, you have a fixed already you have a fixed D. Okay. So depending on the load resistance, there will be now there is no decision taken. So it will directly move from this point to this point. Like what I am trying to say is, suppose you have already okay. So you have already operating with the MPP point with this duty ratio. Now, whenever there is a change in irradiation or increase in irradiation, your new operating point will be this one. Okay, so it will be like right to the MPP point if you increase the irradiation. So that is why your 0.1 is shifted to 0.4. So this is like this point. It is right of the MPP. Now you see what is happening. As per the original P&O algorithm, your del P is increasing greater than 0. Your del V is also increasing greater than 0. So what is the decision we should take? As del P greater than 0, del V greater than 0, we should actually increase the panel voltage. We should increase the panel voltage means we should decrease the duty ratio. So as the decision is we should increase the panel voltage. So this point will move to 5. Okay. But actually it should move in the opposite direction. So in the first, obviously, after that it will automatically, algorithm will reconsider itself and it will move back to the MPP. But at the first instant, it takes a wrong decision, the normal P&O MPPT algorithm. Okay. Now you can consider that there is a cloudy days and the cloud is constantly moving. So suppose you can take a scenario like it will move to 4, then at initially it is taking a wrong decision, it is 5, and when it is reached the 5, again there is a change in the irradiation. So it will again move to 6. Then at 6 it will move to 7. So ultimately it may happen that continuously it will go away from the MPPT point. Okay, for rapid increase in insulation, and this is called the drift problem. Okay. So as I said, the normal P&O algorithm, as the problem, it takes the first wrong decision when there is a increasing irradiation level, because it is not able to understand that the power change is due to the irradiation level. So that is why in one of our work, we actually modified this P&O algorithm by using one simple loop and without using any extra sensor. And that is published in IEEE transaction on industrial electronics. And actually it is not like it is now cited, I think, more than 550 times. It is well cited paper, this paper. Google citation is now around more than 550. So what we did in this modification, as I said, that if you see, if I have a IV characteristics, okay. Now, if I change the duty ratio for a constant irradiation, if your del V is always, if your voltage is increasing, your current is decreasing. Okay. But if there is any irradiation change, then your voltage is increasing, your current is also increasing. So we have used this information that irradiation, if there is an increase in irradiation, then there is also increase in the current level. And as in the P&O algorithm, we are already sensing the voltage and current. So we have just put this extra loop into the normal P&O algorithm. Okay. So this is this is dP greater than 0, dV greater than 0. Till this point, it is the normal P&O algorithm. Now what we are checking is we are checking dP greater than 0, dV greater than 0, both are yes, okay, whether di greater than 0 or not. If di greater than 0, then we can confirm that there is a change in irradiation. And if there is change in irradiation, then actually we should not increase the panel voltage. We should actually decrease the panel voltage. So if dP greater than 0, dV greater than 0, di greater than 0, this means there is a change in irradiation, increase in irradiation. So actually we should decrease the panel voltage. So that is why it is there. Otherwise, rest all are same. It is same as normal MPPT algorithm. Okay. Now, obviously, I think you know. Now you can also theoretically prove that when there is an increase in insulation, your delta V is greater than 0, as well as your delta I is greater than 0. So that is just proven by using some equation. So IPV is equal to V PV by R equivalent. This R equivalent is basically nothing but you can consider the RPV that we have already derived. And then RPV in terms of RL and D, we have already derived previously. So if I put this expression, and this is already from the single diode model, we know the panel current, and panel current in terms of the load resistance, duty ratio, and panel voltage can be expressed in this way. And then if you just expand this exponential term till its first order, then you will get this expression. That VPV panel voltage is basically ISC divided by this whole function. Now this ISC is depending on the irradiation. G is for irradiation. G is representing here as irradiation. And ISCG is basically the STC condition irradiation, and there is a difference in the temperature. And this is the STC 1000 watt per meter square, and this is the any other irradiation level. So if you just do the derivative with respect to change in irradiation, you will see that both the dPV by dG and dIPV by dG, that means the change in the panel voltage with respect to irradiation and change in the current with respect to irradiation, both are positive. Okay. So this is your normal P&O algorithm. Now, if you see here, we have already, so you have you actually want to change the duty ratio with small amount delta D. So how to choose this delta D? Okay, how to choose this delta D? Actually, depending on your, you can simply understand one point is that if I take del D as large value, then what will happen? If del D is large, if I take a large value, then what will happen? When it reaches the steady state, there is a huge oscillation because this 1 to 2, 2 to 3 is basically depends upon how much value of your delta D. So there is a large oscillation around the MPP point if you take large delta D. And if you take small delta D, then oscillation will be less. But what will happen if you take small delta D? Obviously, you have a less oscillation at this point. But if you take a small delta D, reaching from this point to this point will take more time because now your variation will be very small. So if you take large delta D, you have a oscillation steady state around MPPT. At steady state, you have a large oscillation. but you will reach MPP very quickly. And if you take small delta D, it is just the opposite result that you will get. You will reach the MPP very slowly, but when you reach the MPP, oscillation will be less. So, you can actually do some adaptation of delta D. So there are many because this MPPT, there are a lot of research papers available in MPPT. So you can do this one, because if you see, you can do that. This is basically your nothing but your delta D. You can choose this delta D like m into dP by dV. Okay, why? Because dP by dV is what? The slope. So the slope will be large when it is far away from MPP point. And then your delta D will be more. And when you reach the MPP, your slope will be very low. So you have delta D low value. So you can use this one and you can have some scaling factor. So in this way, so there are multiple ways you can do the adaptation. So this is obviously there are some papers which actually discusses this technique. Now another point that I want to mention other than this delta D is how to choose the perturbation. What is the meaning of perturbation? It means I am varying the delta D. Okay, so D plus delta D. So how much time interval I want to vary this delta? So obviously, whenever you are, because this is a converter, no? Okay. So whenever you are changing your duty ratio, depending on the dynamics of the converter, your VPV will require some time to settle. Depending, obviously, as I said, depending on the dynamics. So we should next perturbation, we should give only after settling the panel voltage. So your perturbation time should be such that, as already it is mentioned, it should be more than the settling time of the system for a state changing delta T. So these are the two important factors of MPPT algorithm. Now, this kind of MPPT algorithm, people are saying it's a direct duty ratio MPPT algorithm, as we are directly changing the duty ratio. Now there is another version of MPPT algorithm are there, which are called VREF IREF based MPPT control. What is this VREF IREF based MPPT control? What it is doing is that you can have the MPPT like normal P&O or fractional open circuit, short circuit, or INC, whatever MPPT algorithm. So from that, you can generate your VMPP, which is actually used as V reference, and you are checking the panel voltage, generating the error, use a PI controller, and then accordingly you can generate the duty ratio. So that is called VREF control. And similarly, IREF means from the MPPT you generate the IMPPT, sense the IPV, and through a PI controller you give it to converter. Okay. So this is the small setup that we built long back around 2013 or 14. This is a SEPIC converter we used for that paper. And you can see, as I said, the three-stepping behavior of the panel voltage. So this is basically your panel voltage. So see, the panel voltage is in from here. Panel voltage is increased this point. Again, it is increasing. So then it is decreasing, and again decreasing. So it will moving in this three-stepping behavior. This panel voltage. Now, as I said, that drift problem. So say, for example, at this point, what is happening is your irradiation is changed at this point. Now, whenever there is a change in irradiation, whenever there is a change in irradiation, whenever there is a change in irradiation, so it is at this point, it will take the decision at this point. So if I don't do any modification, as I said, what is the at the first instant when there is a change in irradiation, what it will do? It will increase the panel voltage. So see, this is the panel voltage. So it increases the panel voltage. Okay. And then obviously it decreases. But first instant it takes the wrong decision. Now let us see this. When we did the modification, so at that time, due to the another extra checking of the current, we know that this variation of power is due to the irradiation change, and we should decrease the voltage. So that is why we decrease the voltage. And see the power also. For this case, we got the less power, but we are getting more power in this case. Okay. So this is the modification that we did. Okay, now I can actually discuss about the same thing for incremental conductance MPPT algorithm. So this P&O and INC, you will see n number of research work is there in the literature for P&O. So that is why I try to explain you properly that what is P&O algorithm. Now, if you see this what is INC algorithm? It is basically coming from the same relationship that P is equal to V panel power is nothing but panel voltage into the panel current. And if you do the derivative with respect to panel voltage, then you will get this expression. Okay. And similarly, if I put dP by dV, because at MPP, dP by dV, the slope is 0. So at MPP, this will be the condition for INC. Because why conductance? Because this is I by V. So it is incremental conductance. And at the left, it should be greater than di by dv should be greater than minus I by V. And at right, it should be less than minus I by V. So that is the same thing that we have already. So dP by dV greater than 0 at the right hand side. Sorry, at the left hand side that we have already seen. And at the right hand side, dP by dV less than 0. So this condition is actually same. If I now instead of dP by dV, if I put I plus di dy, they will get this two expression from here and from here. Now, it is claimed in the literature previously that INC is basically better than P&O. Okay, this INC is better than P&O. Why? Because there are two extra checking condition is there in the INC that was not there in the P&O. And what is this two extra checking condition is doing? Now, suppose, say for example, you have dV greater equal to 0, you have di equal to 0. That means what? That means actually you are reaching the steady state. Because when you are reaching the steady state, there is no change in panel voltage, there is no change in current. So see, we are not changing the duty ratio. So what it is claimed in the literature that in the INC algorithm, there is no steady state oscillation because of these two checking condition. Now, it is also claimed in the literature that INC algorithm also drift free. Now, how it is? See, if I have dV equal to 0 and di not equal to 0, because di equal to 0, it is yes, and di not equal to 0 is no. So it will, if dV is equal to 0 and di not equal to 0, it will come to this flow. And then we are checking di greater than 0. If di greater than 0, yes. So what I said that then it should actually decrease the panel voltage. Okay, but here it is not doing it. And also another point is, if you use the digital platform to implement your MPPT algorithm, that is what people are use analog MPPT. You will never get a condition like dV is equal to 0 or di is equal to 0. So we have seen that never these two conditions are actually checking, or it is satisfying. Never dV is equal to 0 or di is equal to 0. So when you implement the INC algorithm, you will see it is almost exactly equal to P and O algorithm with some delay. So there are also, I think, around 2015 or maybe 2017, there are some papers which actually discusses these issues. That what is the difference between P and O and INC, and they prove that there is actually no difference. So INC algorithm is also having the drift, and it also having the steady state oscillation like P and O. So this is one paper that it was published in Indicon conference. So where we are exactly doing the same thing that we did the P and O. We check that the variation in the irradiation or the increase in irradiation by checking whether dV greater than 0 and di greater than 0. Because if both are 0, then we are confirmed that there is a change in increase in irradiation. Now, I don't think I will be covered the whole slides that I have. So I will only cover this, because this is also a very good modification that we did, and it is also published in IEEE transaction on, I think, sustainable energy, and it is also well cited. It was published in 2020, I think 20 or 21. So what I said is that both the P and O and INC as a steady state oscillation, and this oscillation, as I said, that oscillation is depend on the value of delta T that we have chosen. Okay. Then he thought that is it possible, because see, if it is near about MPP, so as we have seen that there is a three-stepping waveform. So around MPPT, it will move around MPPT. So if I see that what is the nearest point around the MPPT point? What is the nearest point around that MPPT? And if I lock at that point, then I don't have any oscillation, and I will almost get the maximum power. But then one thing I should actually consider, that when there is a irradiation change, if the duty ratio is locked at that point, and if there is a irradiation change, I should again it unlocked, because it will operate, it will go to the another operating point, and again I should come back to the MPPT point. Okay. So these two things we have implemented into the steady output and fast tracking soft MPPT P and O and INC algorithm, where what we did, we try to check the steady state oscillation. Okay. And we are locking the duty ratio at the nearest point of the MPP. And then we are checking, is there any changes in the irradiation or not? Whenever there is any change in irradiation, again the duty ratio will be unlocked. And this idea we are implementing in this MPPT algorithm. So that is what I will explain this diagram. Then you can, I think, then you will be able to understand very clearly. Suppose this is the steady state waveform. So this is the three-stepping. So A, B, C, D. So it will start from here, it will go to here, then A to B, B to C, C to D, and again it will like this one. So if you see, if this kind of waveform we are getting, then we can confirm that it is reached the steady state. And these 2 points at the nearest point around MPP, because this voltage and this voltage is decrease and this voltage is increase. So this is away from the MPP. So these 2 points at the nearest point around MPP. Obviously, they will not be exactly equal, but the voltage difference between this point and this point is very, very less value. So the pattern that we are observing here is that there will be very less voltage difference between one successive point, and in between point, one time I will get the difference greater, another time I will get the difference negative. Okay, so this simple idea, we are actually creating this algorithm. Okay, so for that we are basically we are using these 3 variable: count, ident, and the steady, and we are taking this tolerance. As I said, this VPK and VPVK minus 2. That means this is basically your, as you can see, this is your K minus 2. This is K minus 1. This is K. So I am checking K and K minus 2, then it will be very less value. And K minus 1 will be greater than your K minus 2. So this is less than error tolerance, and VPBK is less than, and VPBK is greater than K minus 2. Now, so we have already captured these point values. So suppose this is K minus 2. This is K minus 1, and this is K. This 3 point is V1, V2, V3. We are checking V3 minus V1. Obviously, as I said, they are not equal, but their difference is very less. So we are checking whether this difference is some smaller number that actually we have decided, the tolerance. And we are checking V2 greater than V3 or not. Now, whenever we will get this kind of pattern, we can think that their main steady state is reached. So we are actually start counting. We are making ident to 1. That is basically ident means it is identification. We are actually trying to identify the steady state. So ident is 1, and we start counting. Okay. So when the count is 2, so we start counting. So when the count is 2, then we have this K minus 2, K minus 1. So here we have this K minus 2. Now at this point, when the count is 2 means I am here, here, and then I reached here. This is K minus 2, this is K minus 1, and this is your new K. Which is, as I said, this is V3, V4, V5. So count is 2 means I am starting from here. This is 0, this is 1, this is 2. Okay. And I am checking V5 minus V3. And if this is error tolerance, less than error tolerance, and V4 is, sorry, it is wrong. Actually, I should take V5 is greater than V4. Okay, so this is wrong. Then I am seeing another pattern. So I can increase my ident to 2. And now, so this is count 2. Now I will go to count 4. So again, 3, 4. Here, this is my K minus 2. This is my K minus 1. And this is my K. So V5, V6, and V7. Again, I will check V7 minus V5, and I will check whether V6 is greater than V7 or not. If this is also true, then I can confirm that steady state is reached, and I will operate the duty ratio at whatever at this point. So VMPP is now your VPBK, and IMPP is your IPBK. So now the steady is 1 means it reached the steady state, and it locks the duty cycle at that point. So this is the experimental results that we have. So if you see, it is very easy to understand from here that okay, this is for resistive load and this is for battery load. So we can at least understand one. This is PN2 and this is INC. So you see that, as I said, when there is a irradiation change, after C is equal to 4, it is basically getting locked and there is no oscillation. There is oscillation. Then at steady state, there is no oscillation and you will get the constant power in all the cases. Okay. I think I can stop now because next session will start from 11. I will share the slides with you because we have done with the voltage sensor. I have multiple slides till now. I don't think I will be able to cover all these slides. I have almost another, what I can say, 21, 23, so 22. So it is better to stop it here. Okay. And I will share the slides. If the participants has any problem to understand, then they can write an email to me. Any question till now?
Thank you, sir. So participants. So participants, if you have any query, then you can ask now.
Correct.
Sir, what is this?
Correct. அதில் வந்து 15 4 இருக்கு.
I don't think anyone having any question.
Sir, in the soft MPPT technique,
Yeah.
What percentage will be the change which is happening between the values?
I did not get your point. When
Hello,
I
sir.
am saying it's.
I think your
Compared to the
voice
conventional.
is not audible properly.
My voice?
Yeah.
Now it is audible.
Sir, your voice is audible. From the participants, someone is asking some questions, I think.
No, I got his question. I think he was asking about that. What is the variation in? Are you saying variation in the voltage level or variation in the power level?
Both the voltage level as well as power level.
No, as I said, see, this steady output and fast tracking. Steady output means our main objective is to lock the operating point around the MPP point when it reaches the steady state. So if you use this algorithm, at steady state, there will be no variation if there is no change in irradiation. So you will get almost maximum power without any oscillation. And we are dictating, or we are actually trying to find out, first we are trying to find out that condition, that whether we reach the steady state or not. So that is what I explained in the slide that just hold on for a minute.
Yes.
Yeah, that is why I explained that if you are using any normal algorithm, you have a three-stepping waveform. Okay. So this three-stepping waveform, it has certain pattern. So between two instant, consecutive instant, the voltage variation is very low, and there will be one increasing voltage level, and to see another consecutive, there is decreasing voltage level. Then another two consecutive, we have increasing voltage level. You have to just have that information. So you have to capture this information. So how to capture? So you have to take this 3-point, consecutive 3-point that always you can store. 3 sampling point. Now you just do the difference. And if this difference is very low, and there are some error tolerance we have decided previously, obviously depending on the panel voltage. And if you asking me exactly this number, I don't remember. It is already mentioned in the paper, which is actually published in the Sustainable Energy. So this difference, and then we are checking this voltage and this voltage. But to make it completely sure, see, you can check this one and you can say I am reached the steady state, but it may not. You can have a false steady state. To make it guarantee, what we are doing is that we are consecutively taking another 2 part, this part and this part, and this 3 consecutive appearance of the waveform will make guarantee that it is reached the steady state. And when it's reached the steady state, I am locking at this point. Then there is no variation. No variation in the voltage, no variation in the power. And the variation will be there only if this condition satisfied. That condition is actually there, which is, as I said, which is basically if the voltage and current both are greater than 0 with some tolerance value, both the del PV and del IPV is greater than 0. That means there is a change in the irradiation condition. So then we should unlock. We should use the normal MPPT technique. That is what we have used in this algorithm. Any more question? I don't know I am able to answer your question or not.
Hello, sir.
Yes.
I just gone through your paper of this soft MPPT sustainable energy paper. Sir, you have used the Arduino microcontroller, which is a 10-bit ADC, I guess. But if you have taken, what if it is a 12-bit ADC or a 16-bit ADC? It can take more samples now, sir. Now we can reduce the duty ratio also. I mean the step size. What are your thoughts on it?
See, that idea was not to, obviously, as you said, if you can go to the higher bit ADC, then you can take more samples. But few points I want to mention is, obviously, one thing is that if you change that, see, you can take more sample, but your delta, as I said, that there is one important factor is the perturbation step size. How much internally you want to change your duty ratio. So if there is a sudden delta D, so it will act as a step to the system. Now, according to that, your delta D step, your panel voltage will vary. Okay, that depends upon the VPV by D transfer function. If you linearize the PV panel, actually that was my. There are various ways you can think about it. For VREF control, you need to design the PI controller. So for PI controller, you need to find out dP by dt transfer function. So that means that when there is a change in the duty ratio, there is a panel voltage change. So you should actually give the proper time to settle the panel voltage. Another important factor you tell me, but is there any need of changing the duty ratio too fast? Because irradiation, because the solar, it is very slow system. Okay. So actually you can perturb your duty ratio with 1 second, 2 second variation. It is no, absolutely will not get any, if it is operating around, see, whenever there is a change of duty ratio, you will move to another operating point. And as you said, obviously, if you get the 12 volt ADC, if you delta D is very less, then obviously you have a less oscillation. But our idea in this paper was just to make it zero steady state oscillation, steady state oscillation free.
Got it, sir. Thank you. Thank you, sir.
Okay.
சும்மா எதையாவது சொல்ல வேண்டியதுதான். ஏப்பா சாம்பிள் என்கிட்ட எப்படிப்பா இருக்கும்? நான் எல்லாம் ஆன்லைன்ல போட்டுதான் நான் எடுத்தேன். நானு
Participants, please mute yourselves. Anyone has any more questions? Please ask. I hope there is no more questions from participants. So we'd like to end the session here. And I would like to say thank you to Professor Samanta for such informative session and on MPPT techniques. Thank you so much, sir.
Yeah, thank you.
So now Mr. Anush G. Nair from Tata LC Limited will be joining soon.